Inside every modern laptop, smartphone, desktop computer, advanced AI server, or practically any other high-tech device are cutting-edge microchips such as these CPU, GPU, SoC, DRAM, and SSD chips, each with tens of billions of transistors inside of them. The transistors inside these microchips are incredibly small, with the tiniest features measuring around 10 nanometers or 45 silicon atoms. This feat of science and engineering may seem impossible because, on one hand, each of these microchips is made from connecting billions upon billions of transistors together, and then, on the other hand, each individual transistor is only nanometers in size. Additionally, these microchips are everywhere and in everything, and therefore, they must be reliably mass-produced. So, how is manufacturing such a microchip even possible? These are photolithography tools, and they're the key to manufacturing microchips. However, it's important to note that there are dozens of different types of tools used in the various steps for making microchips, and each one plays a critical role in the manufacturing process. So, to be accurate, photolithography tools are the ones that are used to copy and imprint the nanoscopic patterns of transistors and layers of wires onto a microchip. And therefore, a useful analogy is to think of these photolithography tools as nanoscale microchip photocopiers. Photolithography tools have been continuously evolving to copy and imprint smaller and smaller transistors and circuitry. And in this video, we're going to dive into this state-of-the-art EUV photolithography system and explore the science and engineering inside of it. So let's begin with a quick overview. To start, the EUV lithography machine takes the design of a single layer of a microchip on what's called a photomask and loads it into the machine. Next, a 300mm silicon wafer with a set of prior processes applied to it is placed onto a wafer carrier inside the machine. With both in place, the machine uses extreme ultraviolet light, or EUV, and a set of mirrors to copy the design from the photomask onto a silicon wafer. The wafer moves to the next position, and the microchip design is copied yet again. This copying happens over and over until the wafer is filled with 100 or more microchips, and then a new wafer comes in, and the